Whoops. Come on, thing, connect. Alrighty, so today we're going to start talking about gases this time. So we finished up talking about transitions between states of matter, and we're now going to be starting chapter 7. Yeah, that sounds about right. Where we're going to be talking about gases. And so we kind of, we understand that liquids and solids are pretty similar to each other in that, they're all closely packed and, behave similarly. They have nice intermolecular forces. But gases, we're going to see, kind of do everything the opposite. And so we're going to see that studying them is going to be, we're going to be able to do a lot of different things that we can't do with solids and liquids. So we're going to see that a lot of chemistry that we're going to talk about in future semesters is done in the gas phase, just because it's a little bit easier to work with. So we're going to go ahead and start off by kind of simplifying the world of gases a bit by applying something called the kinetic molecular theory. And all this is a set of assumptions that just makes things a little bit easier to work with when we talk about gases and kind of doing calculations with them. So this chapter is going to be pretty math heavy, just so we've been with conceptual stuff for a while now, so I figure it's time to go back to math, right? These are in no particular order, just whichever order they happen to come into my head, and doesn't really matter. So first one, gas molecules or particles move in straight lines. That's going to be the first assumption that we make. And if they move in straight lines, that just makes all the math easier for us, especially when we're talking about pressure. And we're going to see all of these assumptions that we make, they're not going to be really extreme. They're going to be pretty safe assumptions. So, on average, they pretty much do behave in straight lines, or at least, as a whole, as a gas sample. Alrighty. Collisions between glass particles, I should say, not with, are elastic. Physics term here, that just means no energy is lost. So normally when things collide, they could collide elastically, meaning no energy is lost, or they could collide inelastically, meaning there is some energy loss going on. And so, that could be friction or heat or whatever, but we're going to just assume that when we collide our gases that we're not going to lose any energy. And gases collide with each other all the time. A very, very frequent event here. Alrighty, the next one is that the average kinetic energy is proportional to the temperature in Kelvin. And this is already something that we've kind of dealt with anyway. We've talked about how kinetic energy relates to temperature. And so just kind of formalizing the assumption that kinetic energy is proportional to the temperature. And so just, again, kind of reiterating that the temperature is a measure of how fast things are moving there. Alrighty. 2 more to go. One is that the volume of the container a gas occupies is much, much greater than the volume of the gas particles. And this one is, the container for a gas is typically somewhere around, a million times bigger than the volume of the gas particles. And so we're going to see that we often will just omit any calculations with the gas particles. And so the point of this one is the volume of gas particles is negligible. So this is not something we can do for solids and liquids because those are really close together. And so the volume of, whatever you're looking at is essentially the volume of, your atoms in there or molecules. But for gases, since they take up their entire container, we're going to see that the container is going to be much, much bigger than the atoms themselves. And so we can just say that the volume of the gas particles is negligible, so we don't have to worry about it. And the last one is that gases do not experience intermolecular forces. And this assumption is probably the most wrong of them all, or kind of easiest to disprove, as it were. Because we're going to see that if you take 111, that we have calculation adjustments that we can do for gases depending on their experience with intermolecular forces. But if we assume that all gases do not experience intermolecular forces, then all gases behave the same way. And so this makes it very easy for us to generalize gas behavior, where we don't care about the identity of the gas. We're going to say nitrogen gas, oxygen gas, helium, methane, they all behave exactly the same to each other. And so we're going to see there, again, it's still a reasonable assumption. We're going to see that the differences are not huge for most gases for the identity of the gas. So for us, especially in this course, all gases behave the same. So we're going to be able to do exactly the same calculations for any gas. We're not going to have to change anything. So we're going to see that this chapter really comes down to maybe 3 formulas, but we're going to go through a lot more than that. But we're going to kind of combine them all together. So, cool. Any questions on these kind of assumptions we're going to make? You don't have to memorize these or anything like that, but it's just important to understand that without these assumptions, the calculations we do would not be possible. So, or we would have to, significantly modify them, make them much more complicated. So, if we want stuff to be manageable, these assumptions work pretty well. Alrighty. Often when we talk about gases, there are kind of 4 quantities we look at. And those, you can say are measurements you would take or properties or something. That's what I mean by quantities. So something like that. So one of them we've already touched on is the temperature. So temperature is one kind of quantity of gas that we can measure, that we care about, that's going to be used in our calculations. We've already just seen that we're going to be using the temperature to relate the kinetic energy of our gas sample to the temperature, something that we can measure very easily. For this chapter, we're going to see that it must be Kelvin. We must always use Kelvin in this chapter for temperature. And in case you've forgotten, Kelvin is degrees Celsius plus 273.15. So just keep that in mind. I'll show you a couple of examples where we'll try to use degrees Celsius and we'll end up with things that don't make sense or impossible to solve. So we'll see that. Another one we talk about is the volume. of the gas. And again, this is really the same as the volume of the container. So whatever your gas is inside, if it's in a flask or if it's in a room or a balloon, the volume of your gas is going to be the same as your container. Remember, gases expand to fill their containers. We're going to see that these are typically done in liters. That's our typical kind of unit there, but technically we could use milliliters or meters cubed or whatever, but we're going to see that most of the calculations we do will involve liters. All right. The amount of gas for this we use moles. So we're going to see that when we're talking about gases, we can talk about their temperature, we can talk about their volume, we can talk about how many particles are in that sample. And so all of these three we've kind of talked about before, or they're kind of simple, like volume is not really a crazy concept. Moles I know everybody hates, but that's okay. It's just the way of, remember, telling us how many particles we have in a given mass of a substance, right? It's pretty hard to measure. I mean, you can't measure moles directly anyway because every, different substance has a different molar mass and all that. So moles is a way we kind of equalize the field. We adjust for all the molar mass with that. But again, thankfully for us, since it doesn't matter, moles of one gas behave exactly the same as moles of a different gas. So we're cool. Alrighty. And then the last thing we have is something called pressure. And this one we have not talked about so far in this class. That is going to be, according to physics, it's a force applied over an area. And so, if you're pushing down on a table or whatever, you are applying pressure to it. And of course, we kind of talk about pressure in a metaphorical sense. You're under pressure to, finish your homework assignments on time, and you have all sorts of pressure at work and all that sort of thing. So we kind of have this idea that it's a force applied, right? In this case, it's over an area. Typically with this, though, for gases, pressure is a measure of how often gas particles collide with the walls of the container. So if we want to think about all of these quantities in terms of like a billiards table, that's kind of a classic model for this. So billiards, pool table. You have various pool balls all moving in various directions. They move in straight lines. Whichever directions are going. If we look at, how about this light blue one, we're going to see as it goes towards the wall, it's going to hit it, right? And it's just going to bounce off in the opposite direction after it does so. But there is still a force applied once it hits that wall, or that edge of the container. And so we're going to see that just how often that happens is going to be very strongly related to the property that we call pressure. And so if we kind of think about this billiards table, we can think of the volume as the size of the table. We have the amount, which would be the number of billiard balls. We have the temperature, which is how fast the balls move. And then the pressure is how often the balls hit the sides. And so all of these four together, we're going to see are going to be able to allow us to do very, very useful things with gases and gas calculations. And so what we can work with for pressure, we have unfortunately quite a few units that we'll talk about here. Pressure units. Most commonly for us and other chemists, we use predominantly two different units. However, there are, excuse me, quite a few more. One is preferred by physicists, for example, and one is technically the official unit, but most stuff is still done in other units. So the most common one for us will be the atmosphere, which is abbreviated ATM, which is the pressure of the atmosphere at sea level. So it's just the unit is defined as this. So it is the pressure at sea level. And so if we want to, I'm going to just kind of go down a little bit here. Here's our C. And here we are at sea level. Technically, although we don't feel it because we're used to it, we technically have a column of air that goes all the way to outer space that is bonking us on the head. There is technically all these little gas particles in here which are bombarding us all the time. We don't feel it because we're used to it. We've experienced this every day of our lives. But these are just the entire atmosphere here. And so that's bonking down on us all the time as the gas molecules in the air move, right? And so as they collide with us, that is the pressure we feel. And that amount is equal to 1 atmosphere if we're at sea level. We're going to see the higher up you go, the less pressure you have. Because if you're thinking about, here we are, this is the Earth, here's a mountain. And here is the atmosphere around it. If we're seeing that at sea level, that's about 1 atmosphere, we can see on top of this mountain, that's less pressure there. My gosh, this drawing is beautiful. So the idea here is that if you're on top of a mountain, you have less of a distance between where you are and outer space, right? The higher up you are, the closer you are to space. You have a smaller region of air that's pushing down on you. So there is, in fact, less pressure on top of a mountain or at high altitudes. So we're going to see that that's going to have some effect on things when we talk about boiling points and vapor pressure again and all that good stuff. All right, well, I totally hoped to have left more room, but I didn't. So that's the atmosphere. That's kind of our standard unit. We also have millimeters of mercury. Wow, I can spell this. And this unit comes from kind of an archaic device where something called a barometer, a mercury barometer, would... how it works, I guess we can do this. Here is a cylindrical container, and we have a test tube or something up in it. And we're going to see that if we have a vacuum in here, and we fill this kind of contraption with mercury, which is actually gray, not blue, but we're going to see that the atmospheric pressure pushes down on the mercury, which forces it to go up this tube. Because a vacuum has no pressure. That's what we define a vacuum as. There's nothing there, so there's no pressure. And so the atmospheric pressure on the outside forces mercury up into the tube. And so forced into the tube against gravity. And we see that this difference here, this height of mercury in the tube, is the pressure. And so we see that at the sea level, we see that we have a standard amount of millimeters of mercury. So we're going to see that 1 atmosphere, which is our pressure at sea level, is equal to 760 millimeters of mercury. So if you are, at the beach with your mercury barometer, please don't do that because mercury is terribly dangerous. We now use electronics instead, but this is how it originally was done. You would see that your mercury would rise up to about 3/4 of a meter in its tube. And so it's pretty cool stuff. So you'll see that the mercury would go all the way up, and then poof, there you have your pressure reading. And that is going to be equal to 1 atmosphere. So that is now a defined quantity there. We have another unit called the torr, named after the scientist Torr. For us, it's going to be the same as millimeters of mercury. So isn't that just great? We have 2 names for the same thing. But more formally, 1 atmosphere is exactly 760 torr. So there's a small difference with sig figs, technically. So this is an exact number, so there are no sig figs if we're using torr to atmospheres. But technically, millimeters of mercury to atmospheres, you would need to apply sig figs. Don't worry about it. For this class, we don't care. Don't worry about sig figs for our pressure conversion units here. All right, so for us, torr and millimeters of mercury are identical. So we can just interconvert between them. We don't have to think about it. Okay, so for us, don't worry. All right, so those are the 3 units we use in chemistry. However, we also see in physics other units. We have the Pascal, which is a Newton per square meter. And a Newton is a kilogram meters per second squared. So that is a kilogram per meter per second squared. We don't need to know this. But technically, 1 atmosphere is about 100,000 pascals. So about 10 to the 5th pascals. You do not need to learn these ones. These 2 you should know. The 760, that is a number you should know. That's something we're going to be using a lot. But the pascals, don't worry about. We'll see there's also something called the bar. Where a bar is just 10 to the 5th pascals. This is technically the SI unit, the bar. So you may see readings in bars or millibars uh, pretty frequently in physics or in other areas, but not so much in chemistry. Let's see, what other units do we have? We thought we were done, right? No. We have, if I remember this correctly, another unit called PSI, pounds per square inch. Let me just Google that because I don't quite remember. Atmosphere to PSI. Let's see. 14.7, I did it. Okay, good for me. PSI is something that we see, when we're filling our tires. A car tire is usually around 30 or so PSI. So that's just over 2 atmospheres of pressure that you have inside your tires. Gosh, what other units do we use here? I think that's enough. So many units for pressure. So we can see it's a pretty important concept that has all these different units because the applications of pressure are really, really... pressure does most of the work that we deal with in everyday life. For example, a car moves because of pressure. Pressure is used to do work. And so we can, anytime we're dealing with any sort of expansion or contraction, we're going to see pressure is going to be behind, what's happening there. So these units don't worry about. These 3 units. They're just kind of more for your own information, just so you can kind of maybe have an understanding. You probably are familiar with PSI, and so you'll see that in atmosphere is about 15 PSI or so. So, cool, enough of that. Let's look at relating the volume, moles, and temperature to pressure. So we're going to see that by looking at this, we're going to be able to kind of predict what's going to happen when we mess with certain ones of these. All right, so I have a scenario for us. So I have just gone to the grocery store, and so my car is full of groceries, and I need to bring them into the kitchen. And so I'm going to go ahead and park the car. Here it is. I can kind of draw a car. That's pretty cool. And here's the house. Alrighty. And so, I'm going to go ahead and... I am blue, if you didn't notice. I'm going to take 1 bag of groceries, and I'm going to walk to the kitchen. As we can imagine, this might take a while for me to get all of these groceries out of here. And so, if that's the case, how can I move or get more groceries to the kitchen? Get the groceries in. How do I get those groceries in faster? And we're going to see that we're going to be able to relate this kind of analogy to these quantities. So, if I wanted to get the groceries in faster, how do you think I might do it? There's 3 ways I can think of just to make things happen a bit more efficiently. I'll give you one. Let's see if we can't think of any. I could move my car closer. Right? If I do that, I'll be able to go between the car and the kitchen much more quickly. Easy. So maybe I shouldn't park 3 blocks away from where I live. I should probably park in the driveway or right outside. Maybe that would be smart. That's one way. Can we think of any others? You guys are dead today. All right, fine. I'll give them to you. Another way I could do it, I could just simply move faster. If I'm walking slowly, things gonna take time. But if I run instead, if I run with these groceries, I'll get them there more quickly. And then the last one is I can take more than one bag. Yeah, exactly. Aha, you showed up. Very good. And then, of course, the spam shows up too. Yeah, I guess I kind of asked for this, didn't I? Don't do that. Usually, the spam bot has been fooled by someone putting spaces in their URL. So, go figure. So, yeah, don't click that. Anyways, with these are three things I can do to. Exactly. So if I carry them all at once, it'll make it super, super easy, right? And so we're going to see that doing these, we can relate these to how gases work. So we're going to see that moving the car closer is like adjusting the volume. Moving faster deals with temperature. And then carrying more deals with the amount, which we call N. And so let's look at these a little bit more detail. So if I do this, I'm going to copy this beautiful drawing. Let's look at that first scenario. So if I'm going to move the car closer, lovely artistry, I know. You guys are probably jealous of my skills. Okay, so if I move closer, if I park the car closer, obviously, if we look at the distance between the car and the house, it's going to be smaller, right? So if I get the car closer, I'm going to be able to get this to happen much more frequently. Yes, I can bring the groceries in much, much more quickly. We're going to see that the kind of rate at which I bring those groceries in is going to be our pressure. So we're going to see that I can get more groceries into the house in the same amount of time if I move the car closer. Easy. And we're going to see that it's going to be the same case for volume and pressure. If I am a gas particle bonking between two walls of my container, if I move those walls closer together, everything else the same, I'm going to hit those walls more, right? Just moving things closer, I'm going to hit them more often. That makes sense? So we're going to see that if we decrease the volume, make that distance smaller in between our walls, that means that the pressure will go up. I'll be able to get those groceries in more quickly. And so we're going to see that this is going to be a relationship that's called an inverse relationship. These are inversely proportional, where if one of them goes down, the other one goes up. And so we're going to see it'll be the opposite case too. So perhaps if you know, or if you've watched movies, or cartoons rather, if someone gets a boulder thrown on them, they get squished, right? Pretty common cartoon thing, right? You drop the piano on, Bugs Bunny or whatever, and he gets squished. That's going to be the case. We're applying pressure with the piano or boulder or whatever, and we're making whatever it is very small as a result. So it crushes things. We're going to see that if you were to go and have fun on Jupiter or whatever, where the pressure is much, much higher, you would be flattened like a pancake instantly. So we can see these are related, not only in terms of gases, but also in terms of real life. And perhaps you've seen other cartoons where if you go out into space, you expand and balloon up and explode without a spacesuit. Not exactly true, but the idea is still the same. So if you go where there is no pressure out in space, pressure goes way down, your volume expands. And poof, then you explode. So, plenty of cartoons have done that, right? They take off their helmet and then they swell up and blow up. So we can see that the pressure and the volume are opposites to each other. So one of them will go up while the other goes down. Mathematically, we can say that if we multiply them together, that should give us a constant value. So if one of them goes up, the other one goes down proportionally. And so as a result, they should still equal the same number if you multiply them together. And we're just going to see that we're not going to really look at this one by itself as much, but we could if we wanted to. But let's not. Let's just move on with our lives. We'll see how to apply this in a little bit. All right. So with that, what was our second one? Move faster. Alrighty, so if I'm moving faster, do we think I'm going to get, or we already know, we're moving faster, we're going to get to the house more frequently, we're going to dump off those groceries more quickly, right? So following the same analogy, if we increase the temperature, we're also going to increase the pressure. So the faster things move, the more often they hit the walls. Makes sense, right? This one is usually not difficult to understand. And we were going to call these directly proportional then. If one goes up, the other one goes up. If one goes down, the other one goes down. So if we slow things down, we reduce the number of collisions. If we speed things up, we increase the number of collisions. And so those are directly proportional to each other. And if we were to put this mathematically, we would therefore say the quotient of those two is going to be some constant. We're not going to worry about what that constant is yet. We'll get there. But for right now, just understand that if one goes up, the other one goes up. So we're expecting, if we double the pressure, we'll also double the temperature. Or vice versa. Everything else the same. Alrighty, hopefully that one's not too bad. The last one we saw was moles. And so if we think if I'm taking more than one bag at once, putting them all in a basket and moving them over, I can get them into the kitchen much more quickly, just like before. And, if you think about it another way, the more, kind of billiard balls you put on your table, the more often they're going to hit the walls, right? The more things you have, the more collisions you're going to have. So we're going to see that as moles go up, pressure will also go up for this one. So, more things, more collisions, right? And of course, I guess I didn't write it here, but faster things, more collisions. And so these are also directly proportional. And so just like before, we're going to see that we'll be able to kind of relate these to each other mathematically by dividing them. And so, if we kind of just summarize this section, we saw that P times V was constant. P over T was constant, and P over N was constant, we can lump all of this stuff together. We can put all four of these together at once. And this is finally where we're going to talk about this constant. So we see that pressure is directly related to volume, or rather, directly related to moles and temperature, but inversely related to volume. And so we can arrange those in an equation like this. And we see that this is the constant that we call R, which is the universal gas constant. Universal gas constant. And it has a value of 0.08206 liters times atmospheres over moles times Kelvin. Notice the units of R tell you the equation. So we have a volume unit liters, a pressure unit atmospheres in the numerator. In the denominator, we have moles and Kelvin. So we have the amount and the temperature. And so even if you forget your equation somehow, this is usually an equation that you practice with so much that you will never forget it, but if you somehow do, you can just look at the units of R to figure out the equation. So R is going to be equal to those units, and so that tells us what these are related to. If we just rearrange things, this is often related like this. If we just move NT to the other side of the equation, just to make everything not be a fraction anymore. This is called the ideal gas law. And it relates these four quantities to each other. So this means that given any three of these four, we can find the other one. So this is a very useful equation for us because we can measure pressure directly using electronics or barometers. We know the volume, right? We know what container our gas is in. We can measure temperature very easily as well with a thermometer. However, moles is not something we can measure very easily. And so we can actually relate three easily measured quantities to one that's very hard to do. So very often we're going to use this equation to figure out moles of something. But we could use it to solve for any of these particular ones. Just so you know, also, sometimes this equation is called the pervert equation or pervert law, just because it kind of spells that a little bit. So there you go. It's there as well. Throw that out there. Why not? If that helps you remember it, there you go. And so let's go ahead and take a look at this using this equation. We could see how many moles of hydrogen will occupy, let's say 12 liters at 300 Kelvin and 2.62 atmospheres. As with any word problem, we should go ahead and look at the numbers that were given and see if we can't relate them to variables in equations that we know. So 12 liters If we look at liters, that is a unit of volume, right? So we know that this is going to be our volume here. Kelvin is a unit of temperature. And atmospheres is a unit of pressure. And the question is asking how many moles, and moles is abbreviated N for this particular equation, the amount of substance. And so we have 3 of these variables. We can solve for the 4th one, right? So if PV equals nRT, we can solve for N just by moving RT to the other side of the equation. And we can just plug stuff in. So P is 2.62 atmospheres. Volume is 12 liters. R is our favorite number, 0.08206. Liters, atmospheres, moles, Kelvin. That's the units for R. And then the temperature was 300 Kelvin. If we see our units, atmospheres will cancel, liters cancel, Kelvin cancels. We're going to be left with moles, which is what we're looking for, right? 1 over 1 over moles, which is just moles. And so we just have to plug all this stuff into the calculator, and we'll get our answer, which is going to be, let's do it, 2.62 times 12 divided by 0.08206 divided by 300. We do that, and we get 1.28 moles. And so that's how we can use this equation here. Notice that nowhere in this problem, even though it said it's moles of hydrogen, that hydrogen business doesn't figure into our equation at all. Because we're going to see, again, all gases are going to behave the same as each other. And as so, we can use this equation for any gas. It doesn't matter what it is. And so the identity of the gas does not matter here. However, if I were to ask you how many grams of gas this was, then of course the identity would matter, right? And so that would be the difference if I'm asking for mass. But since I asked for moles, we're okay. Any questions on that one? Alrighty, let's do another couple of them. How about this one? What temperature in Kelvin does 30 grams of oxygen have in a 1 liter container with a pressure of 800 millimeters of mercury? All right, so a little bit more complicated this time. We're still going to be using the same equation, but there's a couple of things that we're going to have to deal with first. So let's go ahead and just analyze the question that we're given and see what we have here. Well, so the question is asking us for temperature. So thankfully we have that written out for us. We have 30 grams of oxygen. So we have a mass. Let's move on for now and we can see what to do. 1 liter. So that's going to tell us the volume. Remember, liters is a unit of volume. And then we have this pressure of millimeters of mercury, though. Well, we know that R has units of liters, atmospheres, moles, and kelvins. So we have something in liters, but we don't have anything in atmospheres, and we don't have anything in moles. And we know we're solving for temperature, right? So we know that we're going to end up with Kelvin at the end. So we've got two things to do here. We need our pressure to be converted to atmospheres. We can't use millimeters of mercury in this equation. We have to use these units that R has. And then we need to find the moles. All right, so we can do those things. (800 millimeters of mercury) we can convert to atmospheres using their equivalents, right? We know that we have 760 millimeters of mercury for 1 atmosphere. And again, we're not going to worry about the significant figures for that conversion. We're just going to keep 3 sig figs for this number. If we do this, 800 divided by 760, we get 1.05 atmospheres. I'm not going to round the number right away, but I will underline it to just keep track that I have 3 sig figs for this number. So we'll not round it yet. All right, and so our next thing is we need some sort of moles, right? And so we've kind of used all of our numbers so far except for that 30 grams. And so we have to just remember that if we know what our substance is, in this case it's oxygen gas, we have a mass, we can convert that to moles, right? By using the molar mass. We know that 30 grams of oxygen can be related to the moles of oxygen, right? Using its molar mass. And so doing this, we get 0.9375 moles. And it looks like we're just going to keep all of those 4 sig figs. Aha. So now we have everything in the right units. So now we can actually solve our equation. So that's really all I can do with this sort of problem, is throw different units at you. You convert them to liters, atmospheres, kelvins, moles, and then you can solve for stuff. So that's really all I can do. All right, so if we do this now, let's go ahead and look at our equation. So if we're solving for temperature this time, it's just if we move N and R to the other side, the pressure was our calculated atmospheres. The volume was 1 liter. We had our moles. And then finally we have our gas constant. Okay, let's check our units out. Atmospheres cancels, liters cancels, moles cancel. We're left with 1 over 1 over Kelvin, which is just Kelvin. And so we can just now go ahead and do this now that we've done all this math. Okay, so let's plug it all in. 1.0526 divided by 0.9375 divided by 0.08206. This is a really cold thing here. Alrighty, and so we get a very cold temperature of 13.68 Kelvin, which looks like we're going to need to round to 13.7 Kelvin. So, very cold sample of gas here. 13 Kelvin is unbelievably cold. But that's what I get for having such a small volume and a fairly large pressure. So, go figure. And so that would be our answer here with the appropriate sig figs. So, looks like we're all out of time for today. If you want, tomorrow we can do an exam review. Though I am getting a COVID vaccine today, so I may be dead tomorrow, just depending if I have the like super tiredness side effect. So um, I may just have to cancel that, just depending how I'm feeling. But if you want to do that, go ahead and put screenshots of things you'd like to go over in our Discord channel for review questions or whatever, and we can do that. Otherwise, we'll continue this next week, and I'll see you then. So I think there's some homework up that'll be due. It's on the intermolecular forces, and then there's a lab sim as well that'll be due this weekend. So with that, I'll see you guys later. Enjoy your weekend otherwise. Wish me luck. Hopefully I will not have any side effects. That would be nice, but we'll see. So, alrighty. Yeah, that's what I predict. That seems to be the biggest thing, is that I'll just be kind of sleeping all day, which is fine. So if I do that, yeah, we'll see. So I'll just let you know in Discord. If I wake up, I'll be like, sorry, dead, no class. So, alrighty, sounds good. I'll see you guys potentially tomorrow. Hopefully, I have good luck. So, alrighty, take care.